Before we go any further, shall we pray? Shall we pray? Our Father in heaven, I want to say thank you for this wonderful time you've given us. Ask you, Lord, to bless each and every individual who is here. May you help us to understand. May you help us to ask questions where we do not understand. And at the end of the day, Lord, if we understand, let the glory go to you. May you continue blessing us in the name of Jesus Christ to pray to you, Lord. Amen. Yeah, so as we continue with our TD, I'm sure you through the weekend, from Wednesday up to the weekend, you passed through the previous questions which we did. Some of you never sent your work. For the first one, I gave you, for the first exercise, I gave you the second and third question to do it. Yeah, some of you never did it, and there are some who did it, but they had challenges. Yeah, so I just wanted to tell you that when you're solving algebra or when you're solving mathematics, you need to be careful. You need to be very careful. Small errors makes the whole question to be wrong. So some of you, almost all of you, it's not that you didn't understand the concept of division Euclidean or what, it's just because you are making errors when calculating. The signs, you need to be careful with the signs, you need to be careful. Yeah, so if you want, you can be multiplying the sign which is outside. You can be multiplying it there, down there when you are doing the subtraction, when you are finding the remainder there, you can multiply it down, or you can be doing the same thing, this minus the one inside, put my brackets. I use the one for brackets because I knew it will not confuse you. Now, if you use the direct one where you multiply the negative that side, when you multiply the two numbers, then you put the negative, sometimes it may confuse you. So I encourage you to be careful. Algebra is simple but tricky. Yeah, so just be careful when calculating. But everyone, so far, all those who sent their work, you know what you're doing. You know what you're doing is just to small errors. Yeah, so and then for those who never handed in their work, I encourage you to do so, because if you do not practice mathematics, you do not know where you'll be making errors. So if you think, you say, no, I understood the concept, but there are errors like the ones your friends were making of signs, whatever. If you don't practice, you will not see those problems of the signs, and then you're going into an exam with the same problem, you make mistake, the whole question is wrong. So practice makes it perfect. So even if you don't hand in, but on your own, try to solve as many questions as possible. So we are on exercise 3, exercise 3. So exercise 3 says soit A et B, les polynômes suivants, A égale x to the power 5 minus 4, x to the power 4 plus 7, x to the power 3 minus 8, x to the power 2 plus 5x plus minus 2. Then b is equals to x to the power 4 minus x to the power 3 plus x minus 1. So the first question says, determine le PGCDA et B. I'm sure you solved this question. It was very straightforward. So you compare with the answers that we are going to find here. You are going to compare with the answers that we are going to find here. Yeah. So the first question says find the PGCD. So we've got R is equals to this, and R is the highest power. We've got B with the smallest power. So this can divide this. So the PGCD, this is our B, this is our R. So the degree of this polynomial is x to the power 4, its degree is 4. its degree is 5. So x to the power 4 into x to the power 5, it will give us what? X. It will give us x. It will give us x. X times x to the power 4 is x to the power 5. X times negative x to the power 3 is negative x to the power 4. X times x will be x squared. X times minus 1, it will be negative x. We'll put our negative outside here. This minus this, it will be 0. It will be 0. Negative 4x squared. This to be plus, right? So negative 4x squared, negative 4x to the power 4 plus x4, it will be what? Negative 3x4, 7x3 minus 0, it will be 7 to the power 3, negative 8x2, this to be distributed here to be minus. You need to be careful with the signs. So negative 8x2 minus x to the power 2, it will be what? Negative 9x to the power 2. This 5x, this will be distributed to be plus. So 5x plus x to be 6x. Negative 2 minus 0 to be negative 2. We check the power here is to the power 4 here, to the power 4, the degree. So this can still go into this. So this into this, it will be negative 3. Negative 3 times this, it will be the same, negative 3x to the power 4. Negative 3 times this, it will be positive 3x to the power 3. Negative 3 times x to be negative 3x. Negative 3 times negative 1 to be positive 3. To be positive 3. So here we've got positive 3. Like terms together, I was putting them with their like terms so that I work them out. This and this, it will be 0. 7x3 minus 3x3. 3x to the power 3 to give us 4x to the power 3. Negative 9x squared minus 0 to be negative 9x squared. This minus this, so to be 6x. This will be distributed plus 3x is going to give us what? 9x. This negative 2 minus 3 to give us negative 5. And then we check this. The degree of this polynomial, the remainder which we found here, is equals to 3. The degree of this polynomial is equals to 4. So this cannot go into this, but this can go into this. So we draw a line and we start another division Euclidean of this into this. So we put the one which is dividing, we put this side. So 4x to the power 3 minus x minus 9 minus 9x squared plus 9x minus 5, which is a remainder one, and our b is x to the power 4 minus x to the power 3 plus x minus 1, which is equals to our b here. So 4x to the power 3 into x to the power 4, it will give us what? 1 over 4x. 1 over 4x times this to give us what? X to the power 4. 1 over 4x times negative 9x squared to give us negative 9 over 4x to the power 3. 1 over 4x times 9x to just give us 9 over 4x to the x squared. This times this, it would be negative 5 over x. We do the mathematics here. Like terms together, so this and this, they'll cancel. Negative 3x plus 9 over 4x to the power 3. It will give us 5 over 4x to the power 3. Because here to be negative x to the power 3. This will be distributed to be plus. So plus 9 over 4x to the power 3 to give us 5 over 4x to the power 3. And then the like terms, careful this it will work with this. There's no n on top with power 2. So this x minus the m minus will be also to be plus. So x plus 5 over 4x. It will give us what? 5 over 9 over 4x. This you just come and drop it with the negative multiplied here, so it will be just be dropped 9 over 4x to the power 2. Then this plus this, it will give us 9 over 4x minus 1. The 1 you just drop it because to be negative 1 minus 0. You just drop it here. Then you check again the power. It's the same, the degree, so this can still go into this. So 4x to the power 3 into this, it gave us 5 over 16. This times this, it gave us this. This times this, it gave us this. This times this, it gave us this. This times this, it gave us what? It gave us this. We do the subtraction. This minus this is 0. Negative 9 over 4x squared plus 45 over 16x squared give us 9 over 16x squared. When you dropped this, 9 over 4 minus 45 over 16x gave us negative 9 over 16x, negative 1 plus 25 over 16 gave us 9 over 16. And when you see here, your remainder, it has a what? Your remainder, it has a coefficient. The coefficients are all the same. So from here, you've already known which one is your PGCD. You just make it unitary just from here. You don't continue for you, because if you want, you can continue until you find 0. But the thing is that at the end, you're just going to find the same answer. So every time when you just reach at the point where all the non-can are just the same, the coefficients, just make it unitary, and that's your PGCD. Along the PGCD, x squared minus x plus 1. That's your PGCD. Are we okay? If we're okay, we can raise our hands. If we're okay, we can raise our hands. Okay. Thank you very much. This was so as I said earlier, when calculating is very important. The signs, and just be careful when you're calculating this. Let me give you a what. Don't be in a hurry when doing the PGCD, because most of the questions which you find in the exam, the first part they will tell you to find the PGCD, and then you'll see how we'll be using it, the second question, because this will be it will help us to solve the second question, you see. So I encourage you, when you're doing the PGCD or you're doing the division ingredient, just be careful, just relax, just be calm, just pangono, so that you don't make any errors, because when you make an error here, everything down will be wrong. So just be calm, just be relaxed. When you find this, the rest, it will be easy. Yeah. So we go to our second question. Says, on the Dwike, moi J est une racine de A et B. Trouver son ordre. So we're going to deduce that negative J is a racine of A and B. And we're going to find its order. Its order just is multiplicité. C'est la même chose. They can use trouver ordre de multiplicité, or they can just start from trouver son ordre. So c'est la même chose. So we're going to we're going to deduce that negative J est une racine de A et B. So in complex numbers, I taught you about we learned about the polar form, and we learned about the identities of J, how J works. That's why I said That's why I wanted to teach you complex numbers, because this is how we're going to use it. This is how the negative j, the j bar, how they work. We're going to understand them here. So on the duike, negative j est une racine de a et b. Negative j est une racine de d, which is equals to x squared minus x plus 1. So first of all, we are going to write this sentence. We know that this is the PGCD which we found. So we know that negative j est une racine de d, which is x squared minus x plus 1. If you want, you can prove it. Put your negative j here. A racine it's something that when you put in a polynomial, it will give you 0. Remember that definition. So when you put a negative j here, what are we going to have here? We're going to have, this is square. So any number, when it's squared, it becomes positive. So here we're going to have j. And then negative j, when you put it here, what we're going to have is going to cancel this. We're going to have j. So we're going to have j squared plus j plus 1. And this, its identity is that j squared plus j plus 1 is just equals to what? To 0. So when we put our j here, it's going to give us 0. Donc j is a racine of d. Donc see, if j is a racine of this, then negative j is a racine de a et b, because this goes into a et b. Are you getting me? Alors, since this is the PGCD, a PGCD is a polynomial which can go into these two polynomials without leaving any remainder. This is the PGCD here. So if j is a racine of the PGCD, it means j is a racine of a and b. We move from there. So we say we want to show that j is a racine of a and b. So, and we find this multiplicity. So the first part, we've shown that j is a racine of what? Of a and b. And the only way you can show is, if you want, you can go direct where you put your r, your r before you differentiate it, you put your r, and then you put your negative j in the polynomial r. You find that it's a racine. But since we've already found this is PGCD, and j is a racine, negative j is a racine of a PGCD, alors automatiquement c'est une racine de a et b automatiquement. So negative j is racine de a et b. So we have solved the first part of saying we deduce. Here we're deducing. So deducing, we've used the PGCD. So they said you deduce that negative j est une racine de a et b. We have deduced. Now it says and trouver son ordre. So we said for you to find this multiplicity, what did we say? This order. We said what? You'll be doing what? So you're going to be differentiating the polynomial and putting your negative j, and you only stop when your negative j is not a racine of that differentiated polynomial. That's when you're going to stop. So the first part, our first polynomial is this, right? So this is x squared negative 4x to the power 4 plus 7x to the power 3 minus 8x to the power 2 plus 5x minus 2. So when you differentiate this, we all know the rule of differentiation. When you differentiate, you drop this here and you subtract the power. You drop this here, you subtract the power. You drop this here, you subtract the power. You drop this here, subtract the power. You drop this here, its power, and you subtract the power. And then you draw, and for a constant, you know, it just becomes 0. So we come, I told you that you should do differentiation and integration in ADIMA. That's your personal work. So you need to have knowledge of differentiation. So when you differentiated A prime is the differentiation of A, it gave us 5x to the power 4 minus 16x to the power 3 plus 21x to the power 2 minus 16x plus 5. And then we put our negative j we need to try if negative j is a racine, and our main goal is for it to give us what? 0. Identities are very important. Identities are very important. You need to keep them par cœur. Par cœur. You need to keep them by heart. So when we put it negative j, when you put it, how is it going to be? This is a what? An even power, and an even power, when you put a negative number of it, it will be positive. So it will be 5j to the power 4. When you put it here, it will just cancel with this, the negative, so it will be 16j to the power 3. You put it here, this is even, so it will plus 21j squared. Here to the negative multiply with the negative, so to plus 16j plus 5. These identities, note, they are very important. J to the power 3 is equals to 1. And the j to the power 3, all numbers that 3 can go into, it will be equals to the power 3. So if here we are if in our polynomial we have j to the power 6, it will still be 1. J to the power 9, it will still be 1. J to the power 12, it will still be 1. J to the power 15, it will still be 1. All the numbers which 3 can go into is equals to 1. Is very important, very important. You need to keep in mind. So you come here to your j. J to the power 3 is equals to 1. And here we can separate this by saying j times j to the power 3, right? J times j to the power 3. And if j to the power 3 is equals to 1, which means we're going to simplify it here. We're just going to have 5j. The j3 has become 1. Very important, the identities. Follow me here. You come to this one is to the power 3, and you say j3 equal a. So we're going to have 16 here. Then 21j squared, just leave it the way it is, plus 16j, you just drop it, plus 5. You like terms together, you put like terms together. So when you 16 plus 5, what is it going to give us? To be 21. We have 21j squared here. It will be
sorry to disturb. Yeah, I've got a question on the j power 3.
Yes, my friend.
Yeah, how is it giving us 1, or is it j power 4 which is giving us 1?
J to the power 3 is equals to what? Is equals to 1. This is an identity, so you need to keep it. That's how it is. J puissance 3 égale a. And what I said here, this can be written in another form. J to the power 4 can be written in a form j fois j times j to the power 1 times j to the power 3. And since we said j to the power 3 is equals to 1, the j to the power 3 will be, you equate it to 1, and you're just going to remain with j to the power 1. And then 5 times j to the power 1. This is what we have here. Are we okay?
Sir, I also have another question.
Yes. They were first, before we go any further, have we answered the question for your friend? The one who asked it. I don't know if it's the same person who's asking.
No.
Oh yeah. The first person first. I need to get the response from the first person. Then you can ask. Is it okay?
No, it's not okay. As in here,
Where?
at first, I think earlier you said that j power 2 is equal to -1.
Now you are confusing E, I, and J. They are two different things.
Okay.
Be careful there.
All right.
Yes. The other one wanted to ask a question.
Yeah. On the first differentiation, it was 5x to the power 4. When you replace it with j, how did it become 3j to the power 4?
The first what?
When you differentiated the polynomial a, it became 5x to the power 4. Then when you replaced x with j, how did it become 3j to the power 4?
3j. You mean here?
Yes.
This is 5. It's not 3.
Oh, I thought it was 3.
No. This is 5. Just the handwriting is 5.
All right, thank you.
You're welcome. Any other question before we move on? Okay.
Big man,
Yes.
I've got a question.
Yes.
What exactly is J, and in what topic do we find it? Like where it goes a bit much more deep.
What? May you be clear? What?
Like what exactly is J? How would you define it?
J is a complex figure, and it's a polar form of complex numbers. So
Okay.
it's just J. That's how the way they named E in complex numbers, you also have J. So you just need to know the values of J and how J works, the identities of J. That's how it is. So you just need to know them per care. You just need to know how it works. You need to know the difference on how I works, and how J works. And you know the identities of I and you know the identities of J.
Yeah. So does J have a specific value? Like the way I is the square root of 1?
No. The values are the same identities which I gave you.
Okay.
Yeah.
All right, thanks.
You're welcome. So we continue like terms together. This is 5J plus 5J plus like term plus 16J to be 21J here. 16 plus 5 it will be 21 and 21J squared. So you put them in this order. They all have the same coefficient. You factorize it, you're going to have J squared plus J plus 1, which is equated to what? To 0. So here you just put 0 to be 21 times 0 to be 0. So A prime negative J is still a racine of negative J is a racine of A prime. You continue, you only stop, mind you, only stop when negative J is not a racine of the differentiated part. You differentiate this. When you differentiate this, it will be 4 times this to give us 20. The power minus 1 to be 3. 3 times negative 16, it will give us what? Negative 48. Minus 1, the power here to be x squared. 2 times 21, it will be what? To be 42. With the power, you subtract x. Then this, it will be negative 16. This becomes 0. Rules of differentiation. Where have you taken the powers? Which powers? KT, I don't know who is KT. Specify which powers. We've got a lot of powers here. You've got the mic there, you can speak. Who is KT?
As in J to the power 5. 5J to the power 4. As in the power just disappeared. I didn't get the explanation to that.
But you are there when I was explaining, or you are there because I explained how we've got identities here. These are the identities that we have. These are the identities that we have. These are the identities that we have here. We said J to the power 3 is equals to 1. So when we put our J here, we've expressed it in here. I said all numbers which 3 can go into the equals to 1. So J to the power 6 is equals to 1. J to the power 9 is equals to 1. J to the power 12 is equals to 1. J to the power 15 is equals to 1. J to the power 18 is equals to 1. That one, keep it by heart. And then we come here, we've got J to the power 4. How can we simplify this? j to the power 4 can also be written in j to the power 1 times j to the power 3. And j to the power 3 is equals to 1. Allow, what are we going to have? We're going to have, where we've got j to the power 3, we're going to put 1. So to be 1 times j to the power 1 to just be j. Then 5 times j, this is the j we have here.
Oh, okay. I just didn't get that explanation.
Okay.
I also have
We'll go to Aprim.
I also have a
Yeah?
question. Yeah,
Yes, yes.
on the first differentiation, we have 5x to the power 4 minus 16x to the power 3. When replacing x to the power x with the j, when the
Negative j.
yeah.
Negative. We are replacing it. Yeah.
Okay. It's fine.
You're
It's fine.
getting it? Okay. Very good. You need to be
But-
careful with how the negative works and how the even numbers work, right? You need to be careful there.
But when
You need to be careful.
where there's 21 there. Okay, it's fine.
Yeah, very good.
I also have another question.
Yes. So who is speaking? TK, KT?
No, this is Ruben.
Ruben. Yeah, Ruben, go ahead.
Yeah, you have given us two identities here. Does it mean these are the only identities which are for J?
No. I gave you in complex numbers, but I was why I wrote them there. I wanted when explaining, I show you because I'm sure they're in your books, in your notes, whatever. That's why I wanted to show you what we used specific here. But you need to know all of them by heart, because when calculating, you need to think to say, okay, if I express this j in this form, is it going to, because you'll be simplifying it with identities. Are you getting it? So you need to know them by heart. But these are the mostly used ones. Are you getting me?
Yes.
Yeah. And then we differentiate this on core. So it will give us 20x to the power 3 minus 48x to the power 2 plus 42x minus 16. And then we put our negative j. When we put it here, this is a prime number, right? So it will be what? The power here is not even. So what do we have here? It will be the negative will go with the j, so it will just negative 20j to the power 3 plus here even. So just here the negative will, just here the negative will go. So what are we going to have? Plus 48j squared. Here we put to be negative j. Here to be negative 42j. Here to be minus 16. Minus 16. And then we put we use our identities. J square we said is equals to 1. So here we're going to have negative 20 plus, here we leave it the way it is. And then here we've got negative 42j minus 16. We add the two like terms, we're going to have negative 36 minus j minus 42j minus 48j squared. J's negative j squared can also be written in a form of negative j minus 1. This equation, j squared, can also be written, this can go this side, this can go this side. So we'll be playing the same equation. This goes this side, this goes the other side. So I'm going to have j squared can also be written in form of negative j minus 1. This is how I've indicated j squared. So negative j minus 1. I multiply it here. I'm trying to simplify it as much as possible so that I reach at a point where I cannot simplify it, and I'll prove that j is not the racing of it. So when I multiply it to be plus 48j, when I multiply it to be plus what? Plus 48. Like terms together, this 48 minus 36 to be 12, Negative 42j plus 48j, it would be 6j, which is not equals to 0. Alors, negative j d'ordre de a. Alors, its racine, its order. So first we prove that negative j is a racine on top, and then its order is what? You get where it's not equals to 0. The power, the differentiation where it's not equals to 0 is its order, the a. So here on 2, on the second differentiation, that's why it gave us not to be equals to 0. Alors its order is equals to 2 the a. If you don't want to confuse yourself with this, you should know that j is a racine in a before it was differentiated. So you count 1, its order to be 1, and then again when it's differentiated for the second time, it became a racine, so 2, and here it wasn't a racine, so it's 1 and 2. That's why its order is equals to 2. But if you just want to use a direct way where it's the differentiation where it has refused, that's your order. So here negative j racine dot the a. Safi. Question 2 is done. Any questions? Any questions? Repeat on the negative j.
I have a question.
Yes, yes.
So are you saying the negative j does not affect the constant, like there are 5 and negative 16?
No, what we're doing, this is a function. Our first function it was a function of r, a function of r of x. That's why we had the 5x here. But here we're changing, where there's x, we're saying what is r in function of negative j. So here there's no any value of x. That's why we can put our negative j. Even the 16 here, there's no any value of x, or there's no any value of j. There will be there's no any value of x, because we are replacing where there's x, we're replacing with negative j.
Okay.
Are you, yeah, you've understood?
Yes.
Okay, thank you. Any other question? The other person is saying, repeat on the negative j. I don't know exactly what you mean. What do you mean?
Where there's negative j minus 1 in the bracket.
Negative j minus 1. Oh, this one. This one here, I said we're using this same equation. We know we've got this equation. We can make j squared the subject of the formula. So for us to make j squared the subject of the formula, this, you can just take this other side, this, and there'll be negative. That's what we've got. J squared is equals to negative j minus 1. This is where we have this. Is it okay? CK, I don't know if it's CK. CK, yeah, is it okay? Yes. The one who asked the question, is it okay? Is it okay for everyone? We move on. We go to the second question.
Yes. Sorry, I have a question.
Yes, you can ask.
On the second differentiation, where there is 20 x to the power 3 and then negative 48x to the power 2. When we replace negative j, when we square negative j, it will give us positive j, right?
Yeah.
And then when we bring it to negative 48, won't it be negative 48, not positive?
Yeah, it will be negative 48. Thank you for the correction, but as you go down, it will not be equals to 0. So that's an error here with, I think I was just in a hurry in writing. It's an error here, but you need to go and correct it. So you need to go and correct it and prove that it's not equals to 0, but it's not equals to 0. That's what you're supposed to know, but go and correct it. Yeah, and thank you very much for the observation. That's very good. You guys, you are following. Yeah, that's true.
Sorry, can you repeat the observation that you just mentioning?
Oh, she's saying here, when we put our negative j, this is an even number, so an even, it will be positive here. So we're just going to have positive j. It will not have a negative to multiply with this. It will just be positive j. So it will be 48 positive j squared. So it will be negative 48, because this negative will not be tempered with the positive j here. That's why here it was an error. I was just in a hurry in calculating. Yeah, I was just in a hurry in calculating. Have you understood? Have you gotten why you're saying it's an error here? I'm sure most of you, when you're going to do it, you would have found a mistake somewhere. So just go and when you'll be writing in your books, making the corrections, take note of this, take note of that. Is it okay?
Yeah, yes, it's okay.
Okay, that's very good. Yeah, so are we all okay? Can we move on?
Oh, sorry, I've got a
your network
question.
your network is not that much. What can you yeah? What's the question? What's the question? You write your question. I can get you. It's cutting. Write your question. Or if you've got a friend close to you, can try to use if it's the same network, I'm sure it's tripping. I can't get you. Can you please write in the chat? If you want, you can in my inbox or just for everyone there. Who is speaking?
Oh yeah, it was me speaking. I was saying that the order
Boss.
when the other differentiation has not proved that J is not erasing. And then the other question is that, is there a way we can prove those identities for J?
To prove them as in how? What do you mean, can we prove them? What do you mean, can we prove them? These are identities. Identities are there to make your work easier. Identities are there where they're just there to make your work easy. That's how they are. That's how they are. They're just making your work easier. The only thing you're supposed to, when they say it's an identity, that's how it is. So the only thing that you need to do, the most important thing, know the identities. Don't worry about can you prove it or do what. No, it's an identity. For them to put it there, they want to see in mathematics, in algebra, is for the simplification of your work. And you have to know that when I reach at this point, this is just equals to 0. But if you want to go any further, I encourage you to go and search and you try to see where the J, how they came up with this equation that is equals to 0. If you want to go deep, but it's not necessary. It's not necessary. Yeah, so we can move on. We can move on.
But on the same one, I think.
Yes.
Can you go back to the answer? Just a bit.
Yes.
I'm saying the answer. Yeah. I think the answer is just okay. But we just have to put where there's positive 48 and positive 48 and positive 48 first and second equation. Then the third one is just fine. You put negative there. So I think the answer is just okay.
Oh, the answer is just okay.
Yeah, we have negative 36 minus 42j minus 48. You put negative, not positive, so it's fine.
All right. Thank you very much for proving. Oh, here. Okay. I think it was in the head. It was just in the head, and then yeah. Okay. Thank you very much, bro, for verifying. Yeah. So we move on. So you're going to find the same thing here. The answer, just change it here. Just change it here. Yeah. Thank you very much. It's very good to
Sorry,
verify.
on the order, I didn't get you properly.
The order, okay, the explanation of the order. I said the order, I said where is j is not a racine of it. You get this differentiation. This is the second differentiation. So it's equals to 2. So its order will be equals to 2 where it has refused to be a racine. Or if you want, you can just be counting that R, it accepted it was a racine, it gave you 0. You count how many equations it gave you 0. So R, it was 0. R prime also, it gave you 0. So that's 1, 2. Here it never gave you, so it's just 1 and 2. So its order again is 2 if you want to use the counting. But if you just want to use the simple thing, just say where the non-can. It's a differentiation. Where it refused, it wasn't equal to 0. That's its order. This is the easy one, the easiest. Sava? On avance? Ça va. The one who asked, is it okay?
It's okay.
The second differentiation must be the first differentiation. The first one is not differentiated, but why are we putting the R prime, which means it's been differentiated? My friend, this is a differentiation of the first of R. That's why I said R prime. This is a differentiation of R. First, we prove that we said negative j is a racine of d. Although negative j is a racine of R and B in a total, because we're starting for R and B. So we've proven that negative j is a racine of R. Then now, let us try for R prime. This is where I started now from R prime. I've already proved that negative j is a racine of R. Now, is it a racine of R prime? This is what we're proving here. Is it a racine of R prime? This is what we're proving here, and we found it is not. So the first racine before it's differentiated, which is what I proved earlier. And that's what the question asked you, to show if it's a racine of R. You can't go to this one when you've not proven that R, before it's differentiated, it's a racine. Are we okay, Ted? Ted, is it okay?
All right. Yes, it's fine.
Okay. Boss, can you, okay, go through the questions more and some network problem. Question 2. Yeah, our friend had some network problems, so we can do it again. So on the negative j attune racine de A et B, negative j attune racine de D is equals to x squared minus x plus 1. So if negative j is a racine of the PGCD, alors automatiquement negative j is a racine of A et B. Therefore, for R, we're studying for R now. We differentiate R. What do we have? This. We put our negative j, we prove if it's a racine. We have this equation, knowing in our head that j square is equals to 1. So here, 5j cut. What can we do here? We can also write it as 5, open brackets, j to the power 1 times j to the power 3, knowing that j to the power 3 is equals to 1. So what are we going to have? we're going to have what? 1. We're going to have 1 times j to the power 1. And so it will be 5 times j to the power 1, which is what we have here. This, it will be 1, so you just drop 16. This, you just drop it the way it is here. First of all, you just drop it the way it is here. You don't use any identity. You drop, since you go step by step, you drop this here, you drop this here. Like terms together, this plus this, it will be 21. 5j plus 16j to be 21, and we've got 21j squared. So 21j squared plus 21j plus 21. We can factorize it. What we're going to have 21j squared plus j plus 1. This is an identity of j squared plus j plus 1 is equals to 0. So we just come and replace here. So 0 times 21 to be 0. So it's 0. Allo, negative j is a racine of a prime. We again on code differentiate this. We're going to have this. We do the same. We put our j. We put our j here. It's a mistake. When we put it here, it will be j. It will not be negative here. So it's supposed to be negative 48j squared, negative 42j minus 16. This is equals to 1. So just put it negative 20 plus. This you put it the way it is. This you drop it. This you drop it. Like terms together. This and this will give you negative 36. And then you got negative 42 minus 48j to the power 2. Allow, what we're going to do here, we can find the identity. We can use an identity of this through this. So j squared can also be written in. This goes the other side, this goes the other side. What are we going to have? We're going to have j squared is equals to negative j minus 1. So we're going to have negative j minus 1. This times this, this times this. What are we going to have? Negative 36 minus 42j. This to be plus 48j plus 48. Then like terms together is going to give us 12 plus 6j. We can no longer simplify it here. I know this is not equals to 0. Donc negative j racine d'ordre de a. Why we are saying it's the 2? Because on 2, when differentiated the second time, it never agreed. Or we can use where we count the number of times j became agreed to be a racine. So the first part, it was when you just put it in a before it was differentiated. The second one, it was when you differentiated it. So it's 1, 2. Hello, you can use that, or you can just use the one where it's not equals to 0, which is 2. Donc, de. Ça va? Lawrence, is it okay?
Oui, ça va.
Okay. That's very good. We're moving together. That's very good.
I've got a question.
You've got a question? Yes, you can go ahead.
The first one, the a prime, the time we're multiplying the negative j with this polynomial.
Yeah.
The signs, are they not supposed to change?
The signs.
I'm saying the signs. Are they not supposed to?
Yeah, they're supposed to be changing. Where have you seen an error?
I thought this one on 5j to the power 4, isn't it supposed to be negative 5j to the power 4?
That's a very good question. That's a very good question. Maybe. What power do we have here? This is 4. And 4, what a rule of even numbers, even powers. All numbers which are all numbers with a presence of an even number, they are positive. All numbers, all letters. So here we've got negative j to the power 4. It will be positive j because of an even here. But if it's an odd number here, it will be negative j to the power 3, and then it will multiply with this, it will give us positive. And then here again we've got an even. It will change just here. So it will be positive j. Are we okay? The one who asked the question.
Yes, I'm now okay.
Does it mean, okay, Renzu, does it mean we only have to replace j to the power 2 with negative j minus 1 in the second derivative of r and not in the second derivative of r? No. Venzu, you move step by step. My main aim is you move, as I said, you move step by step, right? So the thing is that as I was moving here, first of all, I used this identity, right? I used this identity, I simplified it. When I added it, when I used this identity, when I added it, what did it give me? It gave me this. And this, I simplified it to this. That's why I never used the identity of j squared. But when I came here, I need to simplify it as simple as possible. So as I was simplifying it, I reached here, right? It did not click here. So how can I simplify it more from here? I can make an identity of this through this. That's how this was, I changed this to this because I wanted to simplify it as like I wanted to simplify it to its simpler form. But when you come here, as I was doing it, the first part when I did it, I had this, and this. After I did this, I added them. I did this, and this. If you want, you can simplify it here. It will still give you 0. They'll still connect and give you 0, but you make it too long. It will be longer. It will be long, and you find maybe at a certain point you want to take it back again to j squared. Because your main aim is to have this identity again. Are you getting me? You want to have this identity of j squared plus j plus 1, which will simplify your work, right? That's why I did not break the j in the first part, because that's why I did not break the j squared earlier, because my main aim is I want to come up with this identity. So that's why after that, I just left this like this. I already have the j squared, and I've simplified this. I already have the constants, and I already have the j to the power 1. This is now I added this. But when I came here, I first left it, the j squared, but it reached a point where there was nothing I could do. It could not be, I could not factorize this because they're not of the same coefficient, all that. So from there, that's why now I'm forced to simplify this further. Is it okay, Benzo? Very good.
Okay.
Yeah, very good. That was a very good question. That was a very good question. So we... Yes.
So in an instance where we just end in the j squared, is it going to be correct or need to simplify it well?
Because sometimes why you are supposed to simplify it further, because you may find when you simplify it here, you use this, it will give you 0. So when you stop here, sometimes it may not be correct. That's why you need to simplify it as possible, so that even when you say it's not equal to 0, you are sure you've simplified it to the maximum.
Wow.
Yeah. Okay, so we go to our C. Yeah. Anyone if you're not asking, you can switch off your mic. There's someone whose mic is on.
Yeah, I'm asking.
Yes.
What is the answer?
B. Yeah, you're not loud. I can't get you. What?
Where there is April.
Where there's April?
Yeah. We have x to the power 3. And it is negative there.
Negative what?
Negative 16 x to the power 3. It is negative. Now when you come to the second equation, it is positive. Why is it positive?
We're using negative j. The negative, this is an odd number. So this j, when it comes here to be negative j, it will not change. It will be negative j times negative 16. It will give us positive 16j.
Oh, I get.
Yeah. It's the same question which your friend had asked earlier about this, the 5. It's the same question. So when your friends are asking questions, guys, let us be, because you may find it's the same problem that you have. But if you've not understood the question which your friend has asked, just ask. But I'm just saying, be attentive when your friend is asking a question. You may think you've understood the part, but maybe there's some errors that you never, there's some parts where you never. So when your friend is asking a question, so that maybe they don't know whatever, they want to be clear. So you also pay attention to that, because it will help you to understand it further. Yeah. So we go to C. Déterminer la décomposition en produit de polynômes irréductibles de A et B dans R. These are the questions we'll be finding. So now you are decomposing it. You want to decompose A and B in its form irreductibly, until to the point where it cannot be reduced anymore. That's what you are doing now. So how we do it? How we do it? So we say pour B. Oh, anyway, we've not finished. We've not finished 2. We need to do for B. Sorry. So we're doing for B. So we say B is equals to 4 to the power x to the power 4 minus x3 plus x minus 1. We're still on question 2. We're proving if J is a what, right? Is a Racine. So the first one, when we put J into B, we already proved it on top is equals to 0, right? J prime, what are we going to have? We're going to have 4x to the power 3 minus 3x to the power 2 plus 1. We put our negative J. What are we going to have? The negative, this is an odd number, so you carry the J, so it will be negative J times negative times 4, it will be negative 4J to the power 3. And then here it's an even, so it will be J squared, so it will be minus 3J squared plus 1. You know the identity of this, so it will just be negative 4 here, negative 3J squared plus 1 first. And then we, like terms, what are we going to have? Like terms, what are we going to have? This and this. First, since from here I can simplify J into this form, I multiply this here to be negative J, positive J, 3J, multiply here to be plus 3 plus 1. So this it will be 4. So it will be negative 4 plus 4, it will be 0. We just remain with negative positive J, and positive J is not equals to 0. Alors negative J racine d'ordre A de B on this. That's why it's not equals to 0, so it's order 1. I think this is as simple as possible. We can move on. Are we okay? We can raise our hands if we're all okay with how to show that this is a racine of the other. All right, thank you very much.
No, just a question.
Yes.
Yeah. Here it's showing that the racine it's 1. Then that the other one for H2. Why are we not
the racine? Not the racine,
the order.
Yeah.
The order.
Mm-hmm.
Why are we not also getting from the first one, where we proved that x squared plus x plus 1 is equals to 0?
This is the one. If you want, you can use. You just count. It's only this which accepted, which is 1. This refused.
Oh, okay.
Yeah, that was a very good observation. Any other question before we move on, guys? We're not here to perform. As I said, I'm not here to perform, but I'm here to teach. So we only move when we're all okay. I don't want to leave people behind. Are we all okay? Okay.
Another question.
Yes.
Here, for the first one, which we have not differentiated, it has given us 0.
Mm-hmm.
Yeah. Even
you can prove it if you want. In your work, you should prove it. It will give you 0. Mm-hmm.
Okay. So this one, it is considered as 1, right?
Which one?
The one which we have.
Yes.
This one is 1.
We're finding order. Listen. We're finding the order for B. We're finding the order for A. So if we're finding order for B, why shouldn't we consider this? We're starting with B. And then for us to find the order for B, we have to be playing with this non-kind of B. We differentiate it, it's B. So the first one, when it accepts, it's just order. So it's racine. It's like you're, do you know, in other terms, it's like you're decomposing just part of it. When you're finding it, you are just finding the racines which are in B. So it's like you're just finding a part of racines. They've already told you that negative J is a racine, but there are other racines which can go into this. But they've told you maybe there are 2 or whatever, but they've just told you negative J is a what? Is a racine. And you are having a what? You are having this. So for you to find, to decompose this, what are you going to do? It's like you're decomposing. So the thing is, for you to decompose this, if you already know the racines which can give 0 to this B, you just be putting them and differentiating them until it gives you its power, until it gives you its order of its racine. So how are you going to write this? You're going to write it as brackets. You're going to write it as x plus j, x plus j to the order 1 on top. That's its order. So the order on top is equals to 1. And the order of the normal polynomial is equals to what? Is equals to the degree. Here the order is equals to 1. And when you multiply 1 inside, its degree of this racine to be equals to 1. The degree of this, the normal racine is equals to 4. Although it means that it's not only negative j which is a racine of this b, because the order of the racine, the order of its decomposition must be equal to the normal polynomial. You're going to understand it more when you do decomposition. The third question, what we're doing. Is it okay there?
Yes.
Okay, let us go to C. So, déterminer la décomposition en produit de polynômes irréductibles de A et B dans R. So we're going to decompose this and this. Yeah, so we go. What are we going to do? What are we going to do here? So decomposition d'R. So I've added another one. We are going to decompose this in R, in real numbers and in complex numbers. I've added from the question here. In the question, I just asked you to decompose just in R, but I also want us to decompose in C. So in R appartient à R. We're decomposing R in R. Well, first of all, we said negative J racine de R. So we said J was a racine of R of order 2, right? And we know that the imaginary part is not equal to 0 because negative J is a racine of this thing. So the imaginary part is not equal to 0. This is what EM means. Imaginary of negative J is not equal to 0. Is part of that equation. Alors negative J bar racine de R. So this, keep it in mind. If negative J is a racine of R, it means negative J bar is also a racine of what? It also means negative J bar is also a racine of R when we've come to the decomposing part. So if negative J is a racine of it, it means negative J bar is also a racine of order 2 de R. This is very important. Keep it by heart. Alors, we're going to write its equation in this form: x plus j to the power 2 times x plus j to the power 2, which divides R. Alors, this whole thing can divide what? R. And in this form, it's in its complex form. It's in its complex form. And then, so we're going to now to equate R is equals to what? Mind you, guys, we we said identities, they are very important. These identities I gave you, I said x squared minus x plus 1 is equals to x plus j, x plus j, j bar. X squared plus j plus 1 is just equals to x minus j, x minus j bar. So these you're supposed to know them. So the equation which you are going to have for R, the equation which you are going to have for R is equals to x squared minus x plus 1, which you found for the PGCD, it was equals to this, right? No. I know this will be written in a Racine form. It will be written as x plus j squared, because it's order 2, and then x plus j bar order 2 can divise R. So if this can divise R, in its equation, it can be written like this. It will be R is equals to x squared minus x plus 1 to the power 2 QR. QR is the quotient. This is the equation of this when you're decomposing it. So we need to find the polynomial QR. So for us to find the polynomial QR, you need to divide this by this. You're going to find what your QR is. Division Euclidean of this into this. You're going to find what your QR, and you're just going to do the division Euclidean. You're not finding the PGCD for you to stop when you find your remainder to be equal to 0. No. You are going to just find your QR. But there's a formula that I want you to use, which is very straightforward. So the formula that you're going to use is, you're going to say R is equals to this, and your degree de R, degree de R was equals to 5. In the normal, in the equation R, it was equals to 5. And so the degree here must be equal to the degree this side. So the degree here, you multiply this when this squares here. So the degree here, we're going to have 4. We're going to have x to the power 4. So the degree of just this polynomial is x to the power 4. And here we've got a degree of 5. It means the degree of Q1 will be equals to what? To 1. So that if we've got a degree of 1 here, a polynomial which has a degree of 1 times a polynomial which has a degree of 4. When you add, you know that when you multiply two number, when you multiply these two, the powers will just add. So the power here to be here to be 4, and then here to be 1. So 4 plus 1 to be 5. So the power here of R must be equal to the power of its decomposition here. So it means your Q1 will be equals to what? To 1. Your degree of Q1 will be equals to 1. Allow its equation of Q be alpha x plus beta. Alpha has a power of 1. This will be its equation. So our I is equals to be x, is going to be equals to be x squared minus x plus 1 squared here. I forgot a squared because we have a squared for alpha x plus beta. This is the equation. You get your coefficient here. It will be equal to the coefficient of your polynomial R. So your coefficient in the normal polynomial has a what? The coefficient in the normal polynomial, it's 1 here. That's its coefficient. So we said we're just getting for your polynomial the first part of it, which is its first part. It was to the coefficient 1, and it was x to the power 5. And then from the other side, which part here can give you x to the power 5? So here is 2, so it will be x to the power 4. It's only this x to the power 4. So when you multiply this times this, it will give you alpha x to the power 5. So you've made an equation of this to be equal to this. This, when it's multiplied with this, here it's squared, mind you. it will give you a alpha x to the power 5. You simplify it, x to the power 5, x to the power 5. Alpha is equals to 1. So our alpha is equals to 1. What will be our beta? Our beta, it will always be the coefficient of the constant. You just get the value of the constant that you have in R. What is your constant? In R, what is your constant? The value of your R is -2. Allo beta will be equals to what? Beta will be equals to what? -2. Beta will be equals to -2. If you want, you can use another formula. The way it is here, you've got this part and this part. The power, the coefficient of R is equals to 1. So which means here you're just going to have 1. That's how you can take it. Here you're just going to have a coefficient of 1. So your lambda equals to 1. The coefficient of a constant of R is equals to -2. So beta is just going to be -2. Allo, your R will be decomposed in the form of x squared minus x plus 1 squared x minus 2. This is its what? Decomposition. So you finding its order was very important to you. When they told you find this order, it was very important because you are going to use it here to say, first you said if this is a racine of R, it means -j bar is also a racine of R. And this can be written in this form. You know how we write a racine? A racine is x minus its racine. X minus R. We have this equation in the when we are doing the racine of a polynomial. So it's x minus R. What is our R here? Our racine was -j. So the -j will cancel with the negative which you have for x minus R. So it will be x plus j and the x plus j bar, and they've got order 2. So you just put order 2, and these x plus j and x plus j bar, its identity is x squared minus x plus 1. Its identity in real numbers, is this. Its identity in complex numbers is just this. Are we okay? And we said that in R, it's decomposed to its simpler form. A thing is decomposed. This inside is decomposed, is irreducible, because in R we say this one is irreducible when it has a power 2 and a power 1, and for power 2 its discriminant must be negative. That's what we said. Yeah. So this is already decomposed in its form irreducible. Even this is in its form reductible. Alors here you say la factorisation de A dans A is equals to here is supposed to be squared. A is equals to x squared minus x plus 1 squared x minus 2. So da A is decomposed in this form. This is your answer. Here just add to my squared. Just now it's a squared. Even here it's a squared. Yeah. And then we decompose da C. Its decomposition. Da C. If you find in R, I just get this in R. In C, you know that it's supposed to be to the power 1, right? So this is already decomposed in power 1 to its simpler form in C, because it has a degree of 1. And then this polynomial has a degree of squared. It's not decomposed in C. So, but it has an identity. Its identity is x plus j bar. Its identity in complex. So you just come and replace this form. This whole form, you come and replace it with this your j. Here is supposed to be squared, please. You just come and replace it with this identity with squared x minus 2. So you see that the power on the right side is the same as the degree on the left side, is just the same as the degree with your I here. The degree here again to just be the same with your R. So this is an identity in real numbers, in complex numbers, in real numbers, in complex numbers. Ça fait for decomposition in A, We go to B. I don't know if there are any questions.
Oh, I have a question. Here the network keeps on cutting. So I don't know where you got the x plus j power 2 plus x plus j power 2. So could you please just repeat again, because here we're having bad network today, so we're remaining behind.
Okay, so where is we want the whole question, or you just want to know the rest? We've understood how we did the mathematics. We just want to know where this has come from.
Whole question.
So I said
the whole question, please.
The whole question, all right. R appartient à R. So we said negative j is the racine de de R. We've proved it. We said negative j is the racine order 2 de R. If negative j is the racine of order 2, and we know that the imaginary part is not equal to 0, alors, donc, negative j bar racine de de R. Alors, the negative of a j bar, it will also be a racine de R. So if negative j bar is also a racine de R, because this j is an imaginary part, its racine, it will be written in this form. A racine is just the same as it's dividing R. A racine is just the same as its PGCD because it will divide R. So we've got a racine this times this. So it means x plus j squared times x plus j bar squared divides R, because it's its racine. So we've put it in a form of a racine. We've put it in a form of a racine.
Sorry, Mr. Esau.
Yeah.
I understand that we are talking about real numbers here, right?
Yeah.
But why are we bringing in the imaginary part?
J is an imaginary part. We are studying J, which is an imaginary part. We want to simplify our work, we want to decompose. And to simplify our work, we're supposed to use the negative J, because we have already found the what? We've already found the racines of R. We have already concluded that negative j is the racine de R, and using its racines, we can decompose it, because its racine is like, it's just you decomposing that polynomial. But for you to decompose the full polynomial, you have to know all the racines which give you 0, and then when you know their racines, then you can write it in the form of its racines as it being decomposed. But the question has only given us negative j to be its racine. So if it has already given us negative j to be its racine, let us write an equation in its complex number, because negative j is an imaginary part. Its racine form, it will be this. This is its racine form. And we know that x plus j and x plus j bar in real numbers can be written in an identity of x squared minus x plus 1. That is what? That is a real part. So if that's its real part, we replace this, because if this can divide this, in our equation, we are supposed to have R is equal to this with our remainder, or with our quotient, right? This is our quotient. But we're studying it in R. I replaced this with this non-can in R, and I squared it because it's of order 2. Are you getting it?
Yeah.
It's of order 2. So now we've gone back to our R. So we've gone back to our R. If we were saying this can divide this, so for you to find the value of Q, you have to divide this into this. Now for you to divide this into this, first you have to simplify this, you square it inside everything, you have more work. So there's this formula that we're going to use here. This formula says, we know that degree de R is equals to 5. Which one is our R? Our R is degree is equals to 5, right? So degree de R is equals to 5. And since we're decomposing R, it means it's like you're just writing R in its simpler form. So in writing R in its simpler form, the degree of R here must be the same of the degree of its simplified form. We already have its simplified form, its degree is equals to 4, because this, when you spread it here, is going to be, you are going to have the degree to be x to the power 4 here. So here you already have its degree of this polynomial is 4, and the total degree of R is 5. Allow the degree of Q1 to be what? 1. It will be what? It will be 1. So if its degree is going to be 1 here, then the equation which we're going to have in a Racine form, it will be written what? Cube equals to x, not in a Racine form, but the polynomial that we're going to have of a degree 1, you know that it will be a constant which we've named, we don't know, which is lambda x plus beta, this lambda x
alpha
for lambda x plus beta. Our beta is a constant, alpha with our x, and our beta is a constant. So what are we going to do here? We're going to now put the equation. So our R, this decomposition will be in this form equation, knowing that this is our squared here. This is squared, is an error. I forgot to put squared here. This is squared here, as we took it here to be squared. So our equation, for us to find the coefficient here, we just go back to our R. What's the coefficient of our first part of our R? Is what? Is 1. Allow the coefficient of alpha to be equals to what? To 1. And then for the constant, again, we just go to the last part, because this and this, they are just the same, represented in form of the first one and the last one. So you get the non-can of your what, which is the first one, is coefficient is 1. The last one, which is a constant, is coefficient is -2. Allow beta is equals to -2, alpha is equals to 1. Or you can use this equation. You say this R, it is x to the power 5. And this, for you to have x to the power 5, an equation of x, alpha x to the power 5, we have to multiply, we multiply all these with just this thing, because we are finding for alpha. And we realize that only the first part, because when you distribute, this will be x to the power 4. So it's only x to the power 4 times alpha x, which is going to give us what? To the power 5. So this only to the power 4 times this, it will give us alpha x to the power 5. The one only with the alpha. Allow we cancel this and we cancel this, our alpha will be equals to what? To 1. For the beta, again, is the same thing. It's, you go to your polynomial. The second one is, what's the second one? It's -4x to the power 4. -4x to the power 4. So you're going to put your -4x to the power 4. It will be -4x. -4x to the power 4 is equals to what? -4x to the power 4 is equals to what? Which one here it will give you? Which beta it will give you? -4 x to the power -4x to the power 4. So what are we going to have here? When we distribute our 2 here, we're going to have x to the power 4, x to the power 3 here. So this x to the power 4, when it multiplies with the beta itself, is going to give us what? It's going to give us x to the power 4. And this x to the power 3, when it multiplies here, we've already changed it to be, its coefficient to be 1 here. So it will be -x 3 to the times this, it will be -x. It will be equals to -x to the power 4 also, because here is 3, so it will be also -x to the power 4 with this, with our beta here. With our beta here, so what's going to happen? Okay, I'm going to explain this more in the, because as I'll be pointing here, you will not see how the letters go, but to be, I'm going to explain it on this on B, because I used the equation form on B, or on when we're decomposing in B. So for me not to confuse you here, because I'm not writing and it's very difficult for you to follow for B, as for R, as for when I was finding for this, I'd written here. So for now, we'll just use this same formula of saying you just get the one at the end. I'll use this, the same formula. It's the same formula, you can use it for B. I'm going to find the same thing, but since I'm not writing it, so you may not follow. We're going to do it for B. So we go to B. So we say B appartient à R, X. Again, the same thing. Negative J racine d'ordre. Yes?
On the quotient, up. Just a bit up, a bit more up. Square.
Okay.
The form of the quotient that we found was alpha x plus beta, right?
Yeah.
Yes. Now I was asking that is this the form that we're supposed to use, or it will change according to how the equation is?
We'll see it down here, and then you judge. Let us solve B, then you see how it works. Yeah. So we go to negative B. You observe how our Q will be. You should just observe here. So we have negative J racine d'ordre A, which also implies negative J by racine d'ordre A de B. And the imaginary part is not equal to 0, and it needs, because this is a complex form, so it needs complex form, it will be written in this x plus j, by which divides B. Although B will be written in this form for Q. And then we know that this is just equal to what? This in R is equals to what we did here. We know it's just equals to this. So we just come in R, in C is equals to this, but in R, we have to change here. So first we're studying it in R. So first of all, we already know our powers here. This X and X, they'll multiply, so we're going to have power 2. So we're saying degree the B is equals to 4, degree the B is equals to 4, and degree the this part of just this part is equals to 2. So if the degree is equals to 2, so you are saying the total degree of this is going to be the degree of this plus the degree of Q2. So this is our equation which we have. We're saying degree the B is equals to 4, which in the other side to be equals to this degree is equals to 2 plus the degree the Q2. So it will be, this will go the other side, it will be 4 minus 2. So the degree the Q to be degree 2. So allow the equation to start from power 2. So it will be R x squared plus bx plus c. Have you seen that your Q has changed? The one who asked the question. Are we okay? Have we seen have we observed what we're doing, how we're finding the equation of Q? All right, silence shows we are moving together. So
no, can you repeat? Just can you repeat that part again?
I'm saying, what is the degree of B? What we're decomposing is B. And the degree of, this is the equation of B, and the degree of the total here must be the same as the degree on the other side, because it's the same B. Now we're writing it in its simpler form in R. In its form irreducible, we've reduced it, but the powers must be the same. And the total power here of B is equals to 4. And the total power on the other side, we've got this times this, you know that you have x squared. So it will be 2 here, plus the degree of this Q2, which we don't know. So we've got 4, 2, and the degree of Q2. How can we how can we know the degree of Q2? You subtract 4 by 2, with 2. What are we going to have? We're going to have degree the Q is equals to what? to 2. Allow our equation will have a degree of 2. So Q2 will be Rx squared plus Bx plus C. And then from there, these are the last number, the first number, the last number. The first number and the last number, the constant. So for the first and the last, as the equation says, we just use the first is coefficient and the last is coefficient. And here we found 1, here we found -1. So automatically we'll just say this I is equals to 1 and C is equals to -1. Our problem is to find Bx. And then sorry, for the first one here, always this first one, it was very simple. There's no need of the calculation. Just get the first one and the last one. In using this other one, because it never had x, so in using that equation, it cannot work. It cannot work here. It cannot work here because the normal formula we get this, the first one and the last one. But for this one, it can work because there's x, but this one doesn't have. So to be just safe on this one, just use, if you just have a polynomial of a degree 1, just get its coefficient for the first and its coefficient for the last. That's all. This is very simple, very simple. And then for this other one, since it's coefficient, since it's of degree 2, we've got this other part here. The first one, the last one, just get them the way they are. Your main calculation will be on the one on the middle. You just use the same, the one on the middle. You say so you put it first. You found it first when you find this for the 2, you put it in the equation. Then now you find for this one. So after you put it in the equation, you find for this one here. These are the what? So the power of the second polynomial, it was what? The power of the second polynomial, it was what? The power of the second polynomial, it was its coefficient, the part was -x3. So you get everything. This is the second part of the polynomial. The second part of the polynomial. So we come here. We come here. What do we have? We come here. What do we have got? For B, we've got -3x for the second part. So which parts, when we multiply them here, they'll give us to the power 3. So this times the beta itself is going to give us what? To the bx to the power 3. And then the other one, it will be -x times x squared is going to give us -x to the power 3, right? So we factorize, we're going to have b minus 1 with x3. We remove, we're going to have beta is equals to 1 minus 1, because this will be a negative. Here we have -1. So the negative, this will go the other side. So we're going to have b is equals to 1 minus 1. I know b is equals to what? To 0. And then the equation here, I've just remembered. The equation here, if you want to use the equation for this one, what you do first, you put its coefficient. The way we did its coefficient on the last number is -2, right? So you put your -2 here, and then on the other side, which number can give you a constant? It's only this. So this times beta is going to give you beta. This is how this equation came about. So you can also use the equation form, but that's why I said it wasn't necessary. You can just go direct for this and the last one. For the first one, the first one, the coefficient, the first one, the last one, just go direct. But the one for this one, the one on the middle, this one, you have to use the equation so that you work with it. And the way I've said is that after I found the last ones, I put them papa, I put them pa, and then now I make an equation. I go back to my b, and the coefficient and its polynomial of the second degree, the second part of our polynomial is -x². So I'm going to make this with a degree 3. So this times this, it will not work. But this times this, it will be beta x3, and -x times this, it will be -x3. You factorize, you're going to have this, cancel, like terms together, beta is equals to 0. So if our beta is equals to 0, which means this whole part is equals to 0. Allow our decomposition to be x minus x plus 1, x squared d minus 1. when you multiply these powers, it will be equal to power 4. Although this has not yet been simplified, because in R, when you have x squared minus 1, you can decompose it further by using what? A difference of 2 squares. So here, when you define the difference of 2 squares, what are going to have? X minus 1, x plus 1. Although in its simpler form, in R, B is decomposed in this form. And then you just check these. These, the 1 and 1. These are degree 1 and degree 1. And in C, how are you going to get? You already know its identity of this. And this is already decomposed in C. So you just come and change this part, you put it in C, and you say in C to be, and in C you just say da, in C to be x plus j bar, x minus 1, x plus 1. Allow in C is decomposed, and in R is decomposed. That's all. That's all. Any questions? How did the equation of B become x plus j bar? These are x plus j bar. These are the racines. These are the racines, David. These are the racines of B. And the racines of B, they are written in this form. The racines of B, the racines of B with order 1 can be written in this form, because we said even the negative j bar is also a racine. So how do you write the form of a racine? A racine, you write it x minus r. And your r is your racine. What's your racine? Is negative. It will come and cancel the negatives. That's why I say x plus j for x plus j bar. Although we know that each racine can divise b. So if each racine can divise b, in its equation, the polynomial, it can be written b is equals to this with its quotient, and this remainder to be equals to 0 when you divide this into this. Your remainder will be equals to 0 when you divide this into this. It's just the same, you're just finding its PGCD at the end of the day. This is just the same as the PGCD, because when you put it, you had to put the PGCD. Now the thing is that we're not going to use the PGCD form, because we have to use the what? The order. That's why we are told to find this order, whatever, because we have to add this order here. So that's why we use the racine form. And when we put the racine form here, its identity is equals to what? The identity of this in R is equals to this. That's why we change this now in R. We had put it to be in R is equals to this, because we're studying it in R. But when we're going to study it in C, we're going to take it back to in C is equals to this, and it's already in its simpler form. Is it okay, David? David Mulena. Any other questions?
Yes.
It's okay? Any other questions? Have we all understood? That's why as I was saying last time, some of us we learn, we take time to understand. It's not that no, we will never understand. No, don't get discouraged if things you don't understand there and then. But if you understand something, you study it more, ask questions, you ask me, ask your friends, yeah, research. You've got YouTube, research. If you want to watch videos in English, watch French. Just be researching, just research. Your personal way could be more helpful. Otherwise, if things that you discover on yourself, on your own as yourself, you discover them, they remain in the head for a long time. Yeah. So are we okay? Okay. If we're all okay, we can raise our hands. Okay. Okay, thank you very much. So I know and I believe that we are supposed to go to exercise 4. Okay. So what we're going to do is we're supposed to finish our TD so that I give you an assignment. Yeah, I give you an assignment on polynomials today. If we'll finish today, if we will be moving together. But if we not move together, we'll finish when the right time comes. So I'm not in a hurry to finish because it's all about understanding. So it's not all about finishing. Yeah. But I pray we finish today so that we go to fractional rationnel on Wednesday. The other week, we just do TDs. Then that other week, we do matrices, because there are some of you where you'll be going, you'll go direct to matrices, and they'll tell you, polynomials is already done. I know you understand. The fractional rationnel you've already done. That's what they'll tell you. Yeah, so that's why I even want to, at least I just do matrices in the other part, so that even those who be going, who do just matrices, they will benefit. But polynomials are very important because you use them in matrices. Even fractional rationnel, you are going to use it in analysis 2. You're going to use it. Yeah, so I can say the quiz is done. So I'll be here now for questions. I can even stop the recording. The quiz is done. We're going to continue in the afternoons. We'll finish 4, 5, 6. Oh yeah, we'll continue these other questions. So I'm now ready for questions. Questions on from exercise 1 up to exercise 3. Any questions?